Herman Z. Cummins Memorial Lecture that we are hosting at City College of New York. This was a lecture that was supposed to happen last March. Sandoghdar was supposed to visit us and give this lecture, but given the circumstances, we are Sandoghdar for accepting our invitation and agreeing to do this online today. So a little bit of history about Professor Cummins, after whom this lecture is named. Professor Herman Z. Cummins was a distinguished professor of physics at City College of New York from 1974 to 2010. He received his PhD in 1963 from Columbia University and then followed up with a postdoc with Professor Charlie Townes, the inventor of the laser, and then went on to have brief stints at Johns Hopkins University and NYU, and eventually spent most of his career here at City College. He's won numerous awards, but most importantly, he was one of the first people to use laser light scattering to investigate condensed matter systems. He has made seminal contributions to effects, things like ferroelectric phase transitions, exciton polaritons, several awards. I've listed a few here. The Guggenheim Fellow. He was elected to the U.S. National Academy of Sciences in 1996. He was a fellow of the American Academy of Arts and Sciences in 2001. He has been a fellow of the American Physical Society and a fellow of the New York Academy of Sciences. And he was also a Humboldt Senior Fellow. So it's a great honor to have some stellar researchers give talks on this lecture series. We have had several stellar, we have had a stellar lineup, including Jörg Wattrup, Charlie Marcus, Stephen Chu, Albert Lertscheber, and Wolfgang Kettle. And today we have another distinguished speaker, Professor Vahid Sandoghdar. Professor Sandoghdar received his undergrad, he was born in Tehran, Iran, and moved to US to do an undergraduate degree in physics at UC Davis, followed by a PhD in physics at Yale University, where he did some of the most complex experiments that one could think of in those days, which was to send atoms between two metallic sheets and try to understand the Casimir-Poldar effect and the van der Waals forces in those systems. He followed that with a postdoc at École Normale Supérieure, if I'm not mistaken, with Sir Harosh, and went on to do some experiments on whispering gallery resonators, and really introduced this idea of doing quantum optics on small scale structures. And following that, he had a brief stint at University of Constance, where he extended the idea of nanophotonics, really pushing the ideas of scanning probes to study optics at the nanoscale. And then in 2001, he became a full professor at the Swiss Federal Institute of Technology, or ETH. And in March 2011, he became a Alexander von Humboldt Professor and Director of the Max Planck Institute for the Science of Light in Erlangen. He's also the chair in nano-optics and plasmonics and biophotonics at the Department of Physics at University of Erlangen. The thing about Vahid is that he's introduced several concepts of nanophotonics throughout his career, starting from whispering gallery resonators to introducing single molecules nanophotonics. And the thing that has impressed me and a generation of us experimentalists has been the difficulty of the type of experiments he tries to access. It's always been impressive that he takes on the toughest experiments that's around, and then he does solve those experiments or does it properly to the with such rigor and creativity. And so hence he has a big fan following amongst a bunch of us who are experimentalists, and we have been following his career all along. So we're really honored to have you here, Vahid, to give this lecture. We wish it was in person, but we'll definitely have you over another time. And so without much ado, the stage is yours.
Thanks very much, Vinod. That was a very nice introduction. It's a great honor to be able to give this lecture today. And you do owe me a dinner in New York. I will come back to that.
Definitely.
So hopefully this virus will leave us at some point. So let me share my screen. There we go. All right. Yeah, thank you very much for the invitation.
Vahid, I just wanted to tell everybody that if you want to ask questions, please put your question in the chat, and I'll be looking at the chat, so I'll be able to ask the questions as we go along.
Yeah, that would be perfectly fine. Yeah. I understand this is a general colloquium, so I've tried to kind of tune the topic to be something that is basic enough that people from different backgrounds would actually follow. So I'm not going to give too much of a technical talk, but it's going to be really something that even if an undergraduate in physics should follow. But I hope that I can motivate the talk in the sense that you will see that the topic should be of great importance to researchers. Now, I was pleased to learn just now that the person after whom this whole lecture series is named was the person who introduced or did a lot of work on scattering in solid state systems, because as you will see, scattering is basically the core of everything that I'm going to tell you about today. Before I do that, let me just tell you where Erlangen is, or I think everyone by now knows where Germany is in Europe, but Erlangen is a small town. Somewhere you probably know Frankfurt and Munich and Berlin, so you see that at Erlangen somewhere, this distance is about 2 hours. Now, we have about 110,000 people, a typical kind of university town, but it's actually home to some of the biggest global industries like Siemens and Adidas and Puma. But probably the most important thing in Erlangen is our institute. That's our institute, which is not that old. So it was established in 2009. The main emphasis of our institute is, as the name says, science of light. But we've been interested in the interface between optics, but also generally physics and life sciences. And that's why we've established now a new research center, which is a joint effort together with the University Hospital and the University in Erlangen, which is called Max Planck Zentrum für Physik und Medizin, translated Max Planck Center for Physics and Medicine. And so we're quite excited about that. This building is just started to be built. So in the next 2-3 years, 3-4 years, we hope that we can start operation in that new building. Coming to my own group, I'd like to thank the people who are working with me right now, in case I run over and don't get to thank them at the end. So we have really 2 different branches of activities. This has grown kind of organically over the years. The original work, in a way, as Vino mentioned, is more in the area of nano-quantum optics. And so we have the pleasure of working with some permanent staff colleagues. And we have 3 postdocs right now and many graduate students. The next, the newer area of activity that has grown very rapidly in the past 6-7 years is in the area of nanobiophotoниcs. And towards the end of my talk, hopefully you will see why we got into this business and how actually the methods that we have learned about in quantum optics can be employed in doing biophysics. Okay, so let me just, in one slide with very superficial figures, motivate a little bit or tell you that efficiency in light-matter interaction actually matters. When you do optical studies, usually you don't worry about your photon budget. You don't care how many photons it takes to get a certain signal. But what I want to focus on today is that by the time you get to do high-end quantum technology, or even to do high-end biophotonics, it does matter how efficiently you interact light and matter. And in particular, you will see that we're interested in understanding and controlling the interactions of individual photons and individual nanoparticles or atoms and molecules. Okay, so if we get to the very fundamental level of coupling a photon and a two-level atom, that is a kind of a model system for matter. Typically in your quantum mechanics course or physics course, you would nowadays write a Hamiltonian that has this very simple form where the electric field of light interacts with the dipole moment of the transition from G to E. But in this talk, I'm going to try to convince you that the other picture that is just as valid, having to do with cross sections, is very powerful and possibly more useful for the kind of thing that I'm going to tell you about. So let's take a particle, and this particle could be an atom or it could be a larger nanoparticle. But when you illuminate that with light, this scatters some light, and it might even absorb light. As a result, the light that gets to your detector is diminished, is somewhat extinguished. And the amount of light power that would be attributed to that interaction could be written as the incident power times the ratio of the cross-section of this particle or this interaction to the area over which you've confined your light. This is a very general thing that one can write. Now the question is, how does that really work out? We'll come to that in a second. But before we do that, I want to go back to this picture and bring your attention to the fact that you see here that the scattered light I've depicted as a kind of a spherical wave, and the incident light with something that is like a plane wave. On the detector, you would therefore see the intensity of the incident light and the intensity of the light that is scattered. But you have to remember that the signal that you see on the detector can only exist because some electric field from the particle has made it to the detector. So the way we write this is that we write the sum, the signal is the sum of the electric field of the incident field and the electric field that is scattered, the whole thing squared. So you would have the intensities, but you would also have a cross term. And this cross term is what you would know from your scattering theory as the extinction term. This picture is also emphasizing that you have an interference situation. That is, when the phases are just right, you get constructive or destructive interference, depending on your wavefronts. In the case of a classical nanoparticle, the scattered field can be written as some polarizability times the incident field, where the polarizability would be given by this familiar expression. The important thing here now is that the polarizability is proportional to the volume. And of course, the index of refraction of the particle and the index of refraction of the medium do matter. If you match these two, of course, you don't have any scattering. But given that you have this mismatch, this quotient is going to be fixed. And now if you make your particle smaller, this V becomes very small. And at some point, of course, this polarizability, you might think, becomes negligible. The polarizability is connected to the scattering cross-section with in this way, and also the absorption cross-section is connected to the polarizability, but via its imaginary part. So this is all very basic physics that we learn in undergraduate studies. So again, remember that the information, even about absorption, is encoded in the field that is scattered by the particle and makes it all the way to the detector. All right, now what about a two-level atom? Well, if you look in your textbook again, for example, in the book by Loudon, but you find that also in the book by Jackson, in any quantum optics book you would find that, you would see that the scattering cross-section of a two-level system is given by 3 lambda squared divided by 2 pi. So that's almost lambda squared divided by 2. And now the interesting thing is that this is actually a pretty large scattering cross-section, obviously much larger than the physical cross-section of an atom. That's in the ideal case. If you put your atom in a solid state, then because all the atoms and molecules in your solid are jittering around, there is thermal energy at a finite temperature. This transition is decohered, and what you end up having is that the cross-section now is reduced by a factor given by gamma 0 divided by gamma, where gamma 0 is the natural line width dominated by or dictated by the spontaneous emission rate, but gamma is the overall line width of the or the homogeneous width. And typically in a solid, you might have some non-radiative effects, but mostly you're going to have just decoherence and dephasing effects that are dominating the whole thing. So in practice, if you take dye molecules, color centers, quantum dots, or anything, or ions, and put them in a crystal or in a polymer at room temperature, this dephasing rate is something of the order of 100,000 times larger than, sorry, this should be gamma 0, larger than gamma 0. That means that this whole ratio is of the order of 10 to minus 5. And that's why you don't get a lot of extinction from an individual emitter at room temperature. Another thing that you have to keep in mind is that typically, if we go to more realistic emitters, as we do in a bit, you don't have a two-level system, but you might have a multi-level system, for example, in a molecule. And that means that you have a certain branching ratio associated with your two-level system, but you have, again, a kind of a decoherence channel. And we can put that with some fudge factor alpha, which would tell us about this branching ratio. So now you see that that wonderfully large cross-section can be made smaller by several different effects. But if we go back to this large cross-section, because you can have that, for example, if you trap a single atom in vacuum, then the cross-section would really be that large. And now the question is, can we really detect an atom in extinction? That is, to see a shadow of a single atom on a screen. Well, now the question is, are you going to be able to make A small enough that it would be comparable to something like lambda squared divided by 2? And the answer is you should be able to, because within classical optics, we know that we can focus light down to something of the order of lambda over 2. So this A should become comparable, and the sigma over A should go towards unity. This was kind of the outset, the question that we had about 15 years ago, trying to see whether we can detect a single molecule in that way, because up to that point, single molecules were essentially almost always detected via fluorescence. Now, coming back, before I show you the experiments, I just want to finish more of the theoretical foundation. Coming back to that interference picture, one can show that this type of cross-section language is really completely conformed with this interference picture. Namely, in order to really get to that 100% extinction, you have to match the phases or the wavefronts of your incident light and of your scattered light. In the picture that I'm showing you here, upper left, that is not the case. So you're not going to get a perfect extinction because your incoming plane wave is not well matched to a kind of a more of a spherical or dipolar type of emission that you have. But we showed in this paper by doing rigorous vectorial calculations that if you were to take your incoming light and put it into dipolar mode, then you would be able to get 100% extinction from one single point dipole. So that's a pretty profound result because it shows that a single dipole can act like a perfect mirror, because if you don't get any light in transmission, all the light must be reflected. So basically in the interference picture, you're going to have 100% destructive interference in the forward direction and 100% constructive interference in the backward direction. Now, it turns out that if you take a focused beam and take the largest numerical aperture that you can get in the lab and focus it, you should be able to get to something of the order of 85%, 80% extinction. So this is kind of the theoretical background of the type of experiment that we wanted to do a long time ago. And we chose organic molecules as an emitter. I mentioned before, in principle, you can try to do this experiment with atoms in vacuum, but you would have to trap a single atom and fix it, and that's quite difficult. I'll show you that when you work with molecules in solid state, all the trapping is done by the matrix, but you, of course, have other challenges. Now, when I talk about molecules, most of you are familiar with dye molecules more from biology or fluorescence microscopy type of thing. And indeed, molecules were detected and imaged at room temperature already around 93. If you and this is a typical kind of image that you might get from single molecules in an optical microscope. You see that each point is the fluorescence of a single molecule. Molecules generally have a rich structure. You have electronic ground state, electronic excited state. You have vibrational levels associated with it. If you're worried about molecules in a matrix, you don't really care about rotational degrees of freedom, but you do have the triplet states sometimes to worry about. And then, so in a fluorescence microscopy type of arrangement, when you deal with dye molecules, or if you're working with a dye laser, you typically excite with a high energy. There is a fast relaxation. There is fluorescence involved. There might be non-radiative channels, and then there would be an inter-system crossing, and all of that. The kind of dye molecule that you would know in this context would look like this. Typically a carbon backbone, but you often also have nitrogen, of course, hydrogen, and might have a few other atoms as well. Now, these species always bleach, and they also blink. And these are kind of the nasty features that you might know from molecules, and you might think that therefore molecules are not really suitable for doing quantum optics. But in fact, already dating back to 1989, 1990, the pioneering works of W.E. Marner and Michel Horry showed that you can work with molecules in a very stable and comfortable way if you go to temperatures of the order of 1 to 4 Kelvin. And the type of dye molecules that one uses in this situation look more like this. This is a very rigid carbon backbone with hydrogen passivation around it. So if you really want to, you can think of this as a piece of graphene that has been very carefully cut out. Depending on how you've cut out your sheet of graphene, you would tune the resonance to different wavelengths. And these molecules are typically planar and, as I said, quite rigid. And this is why you end up having a very strong zero phonon line. That is, when you go from the ground state to the excited state, you have a very well-defined good transition. But of course, your molecule is still a molecule, so you have vibrational levels associated with the excited state and with the ground state. And that means that you have the possibility of getting redshifted fluorescence. For this type of work, your molecules are embedded typically in an organic matrix, for example, something like anthracene. Then we go to low temperatures. And when you go to low temperatures, each one of these molecules becomes very narrow. So that although you have a certain inhomogeneous distribution of the resonance frequencies because you're in a solid, the individual resonances do not overlap, which means that if you, as I showed here, if you scan a narrow laser frequency across the inhomogeneous band, you become resonant with individual molecules at different times. The other thing that I want to mention is that although vibrational levels of molecules in vacuum could be very long-lived, when you put them in a solid, they become very short-lived. So these states decay within picoseconds. And that means that this channel here is incoherent, but the channel that will interest us in a good part of the talk will be say, main channel, the zero phonon line, going from the V equals 0 to V equals 0, this transition here. Now I'm going to show you a little movie now where you see how in a crystal, you can see the contour of the crystal, individual molecules light up as the frequency of the laser is scanned across something of the order of 50 gigahertz or so. In this particular case, we're dealing with this molecule, which we called dibenzotyrrolene, or short DBT, embedded in anthracene. So the crystal is a crystal of anthracene, and you have some DBT molecules doped inside that light up every time your laser frequency is resonant with them. Now, the first experiment that we did in the way of trying to see whether we can detect a single molecule in extinction, we did actually near field, because we were thinking that, well, we had experience with near field microscopy at low temperatures, and we thought that that would be the one way where we can make sure that light really is confined to an area that is comparable or smaller than the cross-section of a single molecule. So this was actually a difficult experiment because you have quite a few challenges aside from running your near-field microscope in a cryostat. We also had to had challenges of making very thin samples that were stable. But the simple arrangement is as shown here. You have a near-field probe that actually looks like that. So you have a fiber that you've coated with aluminum. You leave an aperture. And this aperture is now smaller than 100 nanometers or so, and that means that light is really confined to that level. And on the right, I'm showing you a typical signal where we saw the first time 6% extinction. And that's because the light that is now coming, that is resonant with the molecule on this transition, gets scattered by the molecule out of the beam. So in transmission, this detector sees 6% less because there was one molecule in its way. Now, that experiment is not very useful, although very interesting from a fundamental kind of near-field physics point of view. There are still very interesting issues that one could address. But we went away from that arrangement because in a near-field probe, you send something of the order of 100,000 photons, but only one of them comes out because you get a huge impedance mismatch, and a lot of light gets absorbed or reflected. Very little of it comes out. So if you're really interested in doing quantum optics, you don't like losses. So we thought, okay, how do we get around that? Let's try to just focus very tightly, because as I mentioned before, one should be able to focus light very tightly down to the level of λ/2. Now, this happens in a typical high-end microscope at room temperature on a daily basis, but that's because your microscope objectives are complex objects that look like this and can correct for all kinds of problems and make sure that light gets focused down to the diffraction limit. If you were to put this object in the cryostat, it would immediately either break or completely misalign. So that's not an option. So we made our own objective that would perform down to the diffraction limit, obviously not corrected anymore like this one is, but it was good enough for us. And you can simply put an aspheric lens and a half ball lens piece of glass, and now we had to prepare the sample right on the flat side of this hemisphere, and without worrying you about with all the details of the experiment, this is essentially the arrangement that we managed to do in the cryostat. Again, you do need a lot of degrees of freedom to adjust these things against each other to make sure that you are in focus and that your beam is not crooked and all of these things. But essentially, you have one A sphere to couple light in and another A sphere to couple light out. And in transmission, we detect the light. And again, we were quite pleased to see that as we scan the laser frequency across one of the molecules that we can select in frequency space, we could see extinction effects of the order of 12%. So that was in 2008, and since then we use this, say, strong or efficient coupling between laser light and a single molecule in a number of experiments that I'm not going to be able to tell you about today. But the point was that we really could show that we are now having coherent interaction or scattering of incoming photons with a single molecule at the level of 10% efficiency. Now, 10% efficiency is quite good, but it's not 100%. So again, if you want to do quantum optics, 10% is not good enough. If you're thinking of doing quantum information processing or making quantum circuits, then 10% is absolutely miserable. So we really need to get to somewhere close to 100%. So we have to now go back to our system and say, why do we not have that 85 or 100% that I told you about? And why do we have 10, 12%? Well, one of the reasons I've already told you in the beginning that has to do with the fact that our molecule is not a two-level system. So our molecule has a choice of coming down via these levels or via the main transition. And in fact, the branching ratio is only of the order of 30 to 50%. So this happens to be the same no matter what emitter you take. There are always other decay channels that bother you, and therefore it's hard to get to a real two-level system. So we thought, okay, let's not insist on that. We'll go back to what quantum optics people have already mastered over the past 3-4 decades, albeit slowly, but by now quite routine. And that's to say that we put the molecule in a cavity. And by doing that, we can enhance this main transition to the point that it becomes a lot faster. And therefore, it will dominate these transitions here. So by putting the molecule in a cavity, you're not doing anything to these transitions because in fact, they're not going to be resonant with the cavity. So those transitions are going to be unperturbed, but the main transition is going to be sped up by a large factor. Now, again, when you talk about cavity QED, you can write the Jaynes-Cummins model and all of that. But you can also look at this with the cross-section picture, and that's a very intuitive, simple picture. Now imagine that you have your atom in the cavity, light comes in, and of course, light circulates back and forth in the cavity. Every time that the photon goes by, there's a certain probability of interacting with the atom, which is given by that sigma over A ratio. But the light circulates by essentially the number of circulation is given by the thinness of the cavity. So you get a certain enhancement, which is given by the thinness, but you also pay a penalty because typically the cross-section of your mode is larger than the cross-section that we had in a very tight focus. So the figure of merit that you want to know how well you're doing once you've put your molecule in the cavity is the finesse divided by the mode area. You can write that slightly differently, and you would see that this is the same thing as saying that you're proportional to the ratio of the quality factor and the mode volume. And by now you see that we've recovered essentially the familiar Purcell factor that is more common when you do cavity QED type of calculation. Of course, in cavity QED, you can also rewrite this a little bit to show that it's the same thing as this parameter that is called cooperativity, where G would be your, sorry, that is again a mistake, your coupling rate, kappa is your cavity loss rate, and gamma is your emitter decay rate. Now, when you do this type of thing, we have this figure of merit Q over V. Typically in atomic physics, one has tried to get higher and higher Qs to get this enhancement to be very large, eventually going to the strong coupling limit. But another way of getting a large enhancement is to go to very small mode volumes. Now, in atomic physics, mode volumes have not been very large, but in solid state physics, small mode volumes have been reached, especially if you're using photonic crystal type of thing. But we wanted to have an open cavity because we need to be able to tune our cavity resonance quite a bit to find those individual molecules that I showed you, because we have this inhomogeneous distribution. And also, when you're working in the cryostat, it's not such a good thing to have very high Qs because the stabilization of the cavity becomes increasingly difficult. So we started working on ways to make very small open Faro-Perot cavities, and the way to go is obviously to get mirrors that are very highly curved with a ratio of curvature that is very small, so that when you bring it close to, for example, a flat mirror, you make very small mode volumes. And so we do this by doing focused ion beam milling at the end of an optical fiber or at the end of a silicon cantilever tip. And you can do that really well so that the surface roughness is completely negligible. And then you can in fact also coat that with many layers of dielectrics to get very high reflectivities. The roughness that you see here is just because of the electron microscopy imaging, where you had to coat this with a layer of metal. So when you make a cavity like that, now we, right, this is the little quick movie of how you actually do fitting of your mirror. So you do this in many layers. You have to polish it with the FIB beam and all of that, but eventually you manage to get a very good mirror. So the system that we have is, again, DBT in anthracene. This transition is at around 780, so you can conveniently use sapphire lasers. What you see here is an optical microscope image of a typical anthracene type of thin flake. You can sublimate this or co-sublimate it so that you have a small doping of DBT in it. And then you can carefully take one of these crystals, which could be only of the order of a few hundred nanometers thick, put it on a highly reflecting flat mirror, and then introduce the curved mirror that I showed you before and create your microcavity. The distance here would be only of the order of a micron or so. And then you use a lens to couple in. This whole thing is in the cryostat, and again, you need many degrees of freedom to make sure that you can align all these things properly. But you can do that using commercial slipsticks these days. Again, I won't go through the details of the experiment, but you're welcome to ask me questions afterwards. So I just jump right into the results. You see here that I have the cavity resonance. It's the empty cavity that I have here. And when I tune the cavity to the resonance of a single molecule, we clearly see that the transmission breaks. That because a single molecule now is changing the index of refraction of the cavity, and therefore the transmission is completely broken. Correspondingly, the reflection on the other side becomes maximum. Now, the good thing about an open cavity is that you can really look at the same molecule with and without the cavity. And this is the molecule without the cavity. You see that without the cavity, we have a very narrow molecule that has line width of the order of 40 megahertz or so. And with the cavity, you have a broadened line. And that, of course, is because we have a Purcell factor of the order of 40. There's a lot more. There are a lot more studies in this paper. I just am not going to be able to go through all of those details. But in a nutshell, what we've done is to show that by coupling a complex multi-level molecule to a microcavity, we forced it to behave like a two-level system. And we have managed to have nearly 100% of the order of 95 to 97% efficiency of interaction between laser light and a single molecule. But we took this one step further and did an experiment where we really used a single molecule as a source of single photons, and then coupled those photons that are coming from a single molecule to the cavity where the second or the first single molecule is sitting. So we're replacing laser light by a single photon source. And for doing that, we couple two different cryostats. In the first cryostat, we do an experiment where a single molecule is detected, excited in a way that we collect photons from it. And these are by definition single photons because it's a single molecule that produces them. We couple them into a fiber, bring them to the other lab where we have the microcavity. And now we just bypass all this laser system and couple the single photon source to the cavity. And we get a signal that is, of course, noisier than the laser signal, but otherwise it looks just like that. And again, I won't be able to go through the details of that, but you should consult that paper if you're interested in these things. So in a way, what we've done now is we've coupled two molecules. One was in the cavity and the other one was not. In principle, you could also couple two molecules that are in the cavity. But the way we've done it so far is quite cumbersome because we have two labs, two cryostats, and it's obviously not scalable. But it would be interesting in terms of making a quantum network to find ways to couple a large number of molecules via a large number of photons to each other. So this, in a way, is kind of like the holy grail for the next 10 years or so. And many groups are trying to work in this way, not necessarily with molecules, but with their own PET quantum emitter. So the way to go is to do on-chip circuitry. And so the way we're doing this is we make nanophotonic type of circuits, for example, nanoscopic waveguides and nanoscopic ring resonators, and we have learned how to prepare our samples on a chip like that, so that these molecules couple to the resonator here. Now, instead of having an open cavity, we have a monolithic ring resonator, but these molecules couple to that just as well. Our Qs are not as high yet. We're working on that. So in this paper, we've reported some coupling efficiency more of the order of 20–25% instead of 100%. And we're working on improving that right now. But the way to go then, once you've improved your Q, is also to try to couple different molecules. And for that, of course, you have to bring them into resonance with each other. Because you remember that in our system, we have an inhomogeneous broadening, and different molecules have different resonance frequencies. But by putting microelectrodes on our nanophotonic circuit, we can tune these resonances via the Stark effect and bring them to resonance with each other. And now we can do this on command if we have electrodes at different positions, because we know exactly which molecule is sitting at what position. Remember the image that I showed you where the different molecules were coming to light as we scan the frequency. So we know exactly where the molecules are sitting, at what frequency they are, and then we address the electrode next to it, and we can tune these molecules to whatever frequency we want within a few tenths of gigahertz, which is sufficient. So this is work in progress, and I hope that in the next couple of years, we can really get to a point where we have the efficiency that I showed you in the open cavity experiment, and we have the integration that I'm showing you here in the chip arrangement. So that's more the quantum optics side that happens at liquid helium temperature. We continue to work a lot in that direction, but there's also a lot of interest in trying to bring quantum optics to room temperatures. Now, when you come to room temperature, you remember that we have this coupling to the matrix, and the fact that the cross-section goes down the drain by about a factor of 10 to -5 or so. But also from detection point of view, let's say from diagnostic point of view, if you're not interested in quantum optics, it's very interesting to detect matter that doesn't fluoresce, because right now, when you do single molecule work or single quantum dot or whatever at room temperature, your gateway to detection is always fluorescence. But not everything fluoresces. Some species absorb, but they don't fluoresce. In fact, that's most of things that you see. If you look at the color of your shirt or your sweater, you have that color, not because that pigment is fluorescing, but that's because it's absorbing. In fact, it's not emitting any light at all. But the point is that there are also objects, for example, a piece of dielectric, that it neither absorbs nor fluoresces. And when I say it doesn't absorb, it means that it doesn't absorb that much. So it'd be interesting to have a way to detect all kinds of matter, no matter what they do. And but because everything scatters, that I mentioned, what you really want to detect is scattering. And in a way, I've been telling you the story of detecting scattering by extinction for the past half hour or so. We did an experiment many years ago where it's kind of a brute force experiment where we showed that you can detect the extinction of a single molecule at room temperature, although you have a signal of the order of 10 to -5, because if you do your experiment carefully, you can detect a signal in transmission at the level of 10 to -5. And that's the story that goes into this paper. And later we extended it to also imaging. So you can consult that. So that's kind of interesting. Admittedly, we haven't really worked on that just because we have been busy doing other things, but this is really an interesting story to continue to try to do absorption spectroscopy at room temperature on individual emitters. So basically, the story that I've been telling you is that you have a light source, you have a molecule, and you see the shadow of it. And that's quite similar to basically doing macroscopic type of bright field imaging, where you are also essentially detecting a shadow. So even if you're doing macroscopic imaging, the equation that you have is really the same interference equation. Now, what we do I'm now making the transition going towards some last examples that I want to show you in the area of biophotonics. And what we do now, typically, partly for convenience, partly for technical reasons, we're going to do an extinction experiment in a folded way. So instead of detecting in transmission, we put, if you want, a mirror or the substrate and detect the light in reflection. So some of the light that is coming is going to be reflected from this interface, and some of the light is going to be scattered by the particle or by your object, and the two of them interfere on the detector just as they interfere in transmission on the detector. Okay, so the physics really doesn't change. This is actually the underlying physics of another line of experiment that we were working on, interestingly, almost simultaneous to the other experiment that I told you of looking at the extinction of a single molecule, but at the time we weren't connecting these things necessarily. So here the goal was to detect very small nanoparticles, in particular small gold nanoparticles. This is in the early days of plasmonics, and we were interested in detecting very small gold nanoparticles. Now, you might go about detecting your nanoparticle by doing dark field microscopy, but in a typical dark field microscope, you don't come below particle size of the order of 20, 30 nanometers. But we found out that if you do the experiment that I just proposed, we could detect particles as small as 5 nanometers. So the experiment is quite simple. Instead of avoiding your background, you actually embrace it. That is, you illuminate your sample, for example, gold particles that are sitting on a substrate. You illuminate that head on. Some of your light gets back reflected. This is what would usually blind you. But that light is not just blinding you, but it's also interfering with the light that is scattered by the particle, because these two are completely coherent with each other. The amount of light that is scattered, we've discussed already before, has to do with the polarizability of the particle. And of course, again, the two signals, this E scattered and E reference, will interfere on the detector. But as your particle becomes smaller and smaller, the intensity of the scattered light scales as d to the 6th, whereas the signal of your extinction term scales as d to the 3rd. So for very small particles, this term is actually negligible compared to this term. You can also think that this term is proportional to E incident, which is a little bit of a homodyne kind of amplification that you're doing. At any rate, for very small particles of the order of 5 or 10 nanometers, you can detect that particle quite easily in extinction, but not so easily in direct scattering. So this was a paper that we looked at. There's a book chapter that I recommend for anyone who's interested in this, because you know, it's very old, very rich, but nevertheless very interesting and exciting physics. When you do this work, you have a challenge, and your challenge is that you have a background. I already mentioned that, you know, you would blind yourself, but the background light is not as much of a problem because you can subtract it. But it turns out that the background scattering that leads to a kind of a speckle is the problem, because when you do your experiment, there's always some residual matter around. And the slightest variation of the index or of the optical path would give rise to this type of scattering signal. And that would mask the signal from the real particle that you're looking at. So this was a typical kind of cross-section when we were looking at a 5 nanometer particle on top of a very flat glass surface. You still see that it's difficult to see the 5 nanometer particles. But you can have a trick, especially if you're doing biosensing type of work. And in doing that, you can use the arrival of the particle as a kind of a lock-in detection, if you want. That is, you have a temporal encoding of your signal. And by doing that, we could show, for example, we can see the motion of a single virus on a cover glass. This is long before viruses were bothering you on a daily basis. This work was done about 12 years ago. But you see that this virus is about 50 nanometers in diameter. The coronavirus is about twice as large, which means that its signal is about 2 to the 3rd times larger. So we're in fact detecting the coronavirus these days in the lab quite easily using this method. But a virus is actually a very large nanoparticle. And many years ago, we wanted to push our sensitivity and we wanted to detect individual proteins. Now, when you look at the protein, whether you look at the weight or you look at the size, either way, a typical protein is of the order of 1,000 times. It has a smaller ISCAT signal than the virus that I showed you. Nevertheless, we managed to have an excellent postdoc, Marek Piliarek, who managed to get this experiment to work when we moved to Erlangen. So I run this movie. You see that as the valve opens, the valve is closed right now, you let proteins come out, and I'll tell you when, or you will see it when. On the left, you will see now there are proteins coming. And every time that a protein lands on the surface of the microscope cover glass, it leaves its shadow. And these images that you see here are treated in the way that the previous image is subtracted from each image to mask that background that I was telling you about. So because the protein comes, the frame looks different from the previous frame, and by doing some image processing, you can detect these individual proteins. So again, a protein is a nanoparticle, a fluffy nanoparticle of about 3, 4, 5 nanometers. It's in water, so its index of refraction is of the order of 1.5, 1.6, water 1.3. So no matter how you look at it, it's an extremely small amount of scattering, but as you see here, you get a very respectable, clear signal from it. Let me not worry about this. So we've shown that we can detect different types of proteins, and some are heavier, they give larger signals, darker shadows, and some are lighter, they give lighter shadows. And the interesting thing is that you could show that your signal is proportional to the volume or to the mass. That is the same thing as saying proportional to the polarizability. And my former postdoc, Philip Kukuran, has his own group in Oxford, and he's collaborated with protein scientists, and they have pushed this to actually try to do kind of mass photometry. That is, you really use this ISCAT signal to measure or weigh individual proteins, and this is very exciting. And just to close, I want to say that in principle now, I don't have time, but this would have been another 15, 20 minutes of talk, but you can now kind of close the loop and can show that you can also do this type of protein detection, again, in a cavity. So in both cases, in the case of my quantum emitter and in the case of my classical nanoparticle, I hope I've convinced you that you can get very efficient direct extinction signals. In the case of the quantum emitter, I showed you that we can enhance that by putting it in a cavity all the way to something like 100%. In principle, you can imagine that you can also enhance your signal from a protein by putting it in a microcavity and getting even more signal out of it. Now, there are groups that do that. And if you write down the equation, you could show, for example, that the shift that you would get from the resonator would be proportional to the polarizability. We've talked about that, would be inversely proportional to the volume. If you rewrite that, you could again show that you have a figure of merit, which is Q over V. So the physics is really quite parallel. It's not so surprising because the Purcell effect is not necessarily a quantum mechanical effect. But in practice, so far, I would say our ISCAT biosensing is really the most convenient and the most practically applicable method. When you go to high Q or cavities or very small cavities, it might be intellectually kind of interesting to go in that direction for biosensing, but in practice, you run into lots of problems that this ISCAT method avoids. So I'd like to finish by flashing this mini review for those who might be interested in some of the things that I've talked to you about. And thank you very much for listening. And I'll be very happy if there are any questions.
Thank you, Vahid, for that fantastic talk and introducing us to some new spectroscopic techniques.
I have a question on, you had a slide up on supercontinuum. Very quickly, you passed it by. Okay, could you put that up again? What did you do? Yeah. That's the one. So what did you do on this gold nanoparticles?
Just detect gold nanoparticles, but also to detect their plasmon resonances. So we needed to have an intense white light that we could focus very tightly. And that's really what we did with the supercontinuum.
I see. That was done in 2004. Okay.
Yeah.
Thank you.
Mm-hmm.
Vahid, there's a question from Ming Shu, who wants to know if ISCAT works in transmission geometry.
Yes, absolutely. If I bring this slide, oops. So this is really the same geometry, okay? What we call ISCAT is really when you detect extinction from a nanoparticle. You can do the extinction in transmission, which was the first half of my talk. We did that with a single molecule, but you could imagine that a nanoparticle has more signal than a single molecule, so it's actually easier. Or if you fold it at this point about the place of the particle, then you do this in reflection. And we typically do this in reflection because in a kind of a biophysics type of geometry, it's convenient to work with an inverted microscope, and so you can have access to your sample from above, and then from below you're looking with your microscope objective. But you might as well put a detector in transmission. And in fact, I showed you this experiment that we did when we detected a single molecule. So this is nothing but ISCAT in transmission.
So maybe can I follow up with your?
Yes, Ming-Shu, go ahead.
Yeah. So, you know, currently the so-called quantitative phase imaging is in the transmission geometry, looking at phase directly. I think you also basically made a phase to some degree similar. So I think my question should be, what are really the difference between iSCAT and the so-called quantitative phase imaging QPI? What's really the difference here? Because the
difference between, I'm not sure if I heard you right, the difference between iSCAT and quantitative phase imaging.
Mm-hmm. Yeah.
Yeah, no, they are, and that's why I really recommend this book chapter that I flashed. These are all cousins. Quantitative phase imaging, I mean, look, if you look at DIC, if you look at phase contrast, if you look at quantitative phase imaging, if you look at holography, they all have the same equation as iSCAT. In fact, I try to emphasize that even normal bright field microscopy has the same equation as iSCAT. The thing that makes iSCAT the way we do it, I guess, different, although there's really absolutely no new physics in it, is that we've pushed this to the detection of nanoparticles. Quantitative phase imaging has come more from the holography side or from the macroscopic side. And they've done a lot of very interesting work, but they haven't really put so much emphasis typically on sensitivity. But that community is also moving towards the same direction as we're doing. And at some point, then you can't tell the difference between these things. You can do your iSCAT in the way that, I mean, the way we do the iSCAT in this arrangement, it has the advantage that the reference beam or the reference arm in your interferometer is self-aligned. So it's a very stable interferometer. But in principle, you could separate your reference beam and your signal beam, and that way you can play with your phase as much as you want. But in practice, it's extremely difficult to reach the level of sensitivity that we reach if you have an external reference.
Yeah, you're exactly. I think that's your advantage, because I do believe that QPI will not be able to see nanoparticles at all at this size, 4 or 5 nanometers. So if in the transmission geometry, you will not have a huge E node as a reference beam there. So I think you're going to fail to see that 5 or 4 nanometer particles you want to see. Only work inside the backscan geometry, I think. So that's really actually the first question. I think it may be the iSCAT will not work as well in the transmission geometry when you lose that huge enhancement from the reference beam.
No, that's really not true. I mean, as long as you reach your shot noise limit, which is where you want to be normally, and we get very close to the shot noise limit in a typical experiment, then it really doesn't matter what kind of reference you have. That is, the strength of the reference determines how much contrast you have, but it doesn't determine the signal to noise ratio, because the reference introduces noise and introduces contrast. Again, in this experiment, we're detecting a single molecule in transmission, and the contrast of the single molecule is much smaller than a 4 or 5 nanometer particle.
Yeah, thank you.
So Vahid, there's a question from Ling, and she wants to know if it's possible to separate different proteins, and also is it possible to detect the sequence?
Your connection was not very good. I got the part that whether it's possible to distinguish different proteins, and then there was a second part.
So the second part is, can you detect the sequence of different proteins?
Oh, I wish we could. What we're sensitive to in this method is really just the polarizability. We have no other information. Now, having said that, the polarizability is if we go back to the beginning where we talked about the equation of the polarizability, if you look here, you see that the polarizability has to do with the index of refraction, that is the kind of electron density of your material and of your surrounding. But it also has to do with the shape of the particle, which doesn't show right now in this equation, but this is because this equation is derived for a spherical particle. If you were to put an elliptical particle or a rod or something, then you would get a form factor in the denominator here. So there is some hope that we can tell something about the structure of the protein, but we can only detect the overall amount of scattered light. And the sequence is most probably not going to make a difference there. So we can tell the difference between a protein that is 50 kilodalton or 60 or 70 kilodalton. But we can't tell the difference between two proteins that are both 50 kilodalton and have a different conformation or a different structure.
So Vahid, I had two questions. The first one is, in all of these, you're using a Gaussian or a plane wave excitation. What happens if you have a structured beam, like a beam with an orbital angular momentum or some sorts of beam? How do you gain anything on that front?
It would definitely be interesting. I'm not sure if we gain anything. Again, I won't go as far as saying you will not gain anything, because I haven't thought about it too much. I mean, the thought has occurred to us, but I haven't seen an obvious immediate advantage of doing that. Again, the thing is that with the existing methods, we take the detection almost to the shot noise limit, and we're detecting very efficiently. Now, you know, maybe there's a clever way of doing something somewhere, but I can't think right now that structured light would give me a major advantage. I mean, you know, in practice, in your experiment, it might be useful to have your structured light, but in terms of improving the sensitivity,
or maybe even the species that you're looking at, if it has some kind of a chiral property, there might be, maybe there is.
Sure, if it does, then you're in business. The kind of thing that we're looking at right now is not that exciting. We really have a protein that is, I mean, what the Oxford group has shown, because they have really looked at a lot of different types of proteins, is that they don't seem to see any signature that a slightly elongated protein is giving a different signal than a protein that is coiled. But at some point that must come out.
So another question is about the quantum optics experiments that you did, and your whole idea of having multiple molecules all talking to each other through this cavity coupling. So first question is, you have an inherent inhomogeneous broadening, and is there a way to overcome that to see something akin to Dicke superradiance?
You can prepare your sample to make your inhomogeneous broadening very small, or you can prepare it in a way that you make your inhomogeneous broadening very large. So typically, if you have a very good sample, you could have an inhomogeneous broadening that is of the order of 10 to 20 gigahertz. And the line width of these molecules is of the order of, let's say, 20, 30 megahertz. So the homogeneous to inhomogeneous ratio is of the order of 1,000. When we work with these systems, we don't care about that right now. So our factor is more like 10,000 or 100,000. That is sometimes advantageous for us. But if you, to get that inhomogeneous width smaller, you have to make extremely good crystals. But I don't know anyone that has gone much beyond that. I think that, you know, there used to be a generation of people who had all kinds of tricks about making growing organic crystals, and I'm not an expert on that. And it might be possible to play with that a little bit. But the way we're thinking about this is that we end up having lots of molecules that are not resonant with each other, but by having those electrodes, we tune a controlled number of them into resonance with each other, so that then you do reach the kind of effect like superradiance that you want with a controlled number of molecules.
And these resonators are the ones that are like the ring resonator type geometries, correct?
Yeah. I mean, the jury is out. Exactly in what geometry we'll do this at the end, I don't know. We're just submitting a paper where we're looking, for example, at gallium phosphide nanoguides. So far, we've worked with titanium dioxide. There's a little bit of technology development to make your nano circuitry to be very efficient. It all looks good, but I think we need maybe another year or so to get to a point where we couple more than 2 molecules with each other.
Nice. Okay, thanks, Vahid. There's one more question from, there's a couple of more questions. Alex Punuz has a question. Alex, do you want to ask the question? Alex? So Alex's question is about the diffraction limit being 200 nanometers, and how is it that you're able to beat that to get few nanometers?
We didn't really beat that. We didn't get to, I'm not sure exactly what he refers to as beating it and getting to a few nanometers.
Well, you're seeing something that is few nanometers. So
yeah. So we're not resolving things at the level of few nanometers, right? I mean, that's the important kind of distinction between resolution and sensitivity. A lot of microscopy in the past few years has been emphasizing on resolution, but resolution is only one parameter when you're doing your experiment. Quite often, sensitivity is a lot more important, because if you play with your concentration, for example, you only have one particle or one particle that is moving, then you don't really care about resolution. But sensitivity is the important kind of figure of merit there. So we see a small particle because the polarizability of that small particle is large enough to give us that detectable shadow, if you want. But we're not resolving 2 proteins that are close to each other. We're not resolving them.
Thank you. My headset had given up, so I couldn't talk. Thanks very much.
Did I answer your question?
Yes.
So I guess there's one last question. Could you comment on quantum optics in biology?
You mean whether there are quantum effects in biology?
Or the use of quantum optics in biology, maybe even from the imaging standpoint.
So look, I mean, I think there have been in the past 10 years or so many efforts and many papers where one tries to see whether there are quantum effects or even quantum optical effects in biology. A typical example is the issue of photosynthesis and light harvesting complexes. I'm not sure if that's quantum optics. So if you have a light harvesting complex where you have some kind of an excitonic behavior, a kind of a delocalized state that is doing its job, then you could say that's quantum physics. Obviously it is. The moment you talk about a molecule, it's quantized. So in that way, there's quantum physics everywhere in biology. But I think a lot of times the question is whether things like entanglement and coherence, quantum coherence, play a big role. And maybe I'm not an expert on that, but my impression is that there is no real, say, clear evidence right now that those things are playing central roles. And there are other examples where people look at, for example, magnetic effects in birds navigation or things like that, and then you would think, okay, there must be some kind of a at the molecular level, some kind of a quantum effect. And for sure, again, if you break down a biological system, at the end it consists of molecules, and sometimes quite clever arrangements of molecules where quantum mechanical things like hybridization and all of that, of course, play a role. But if you want fancier, again, entanglement type of things to play a role, I don't know of any system where that is supposed to be happening, but we're not working on that. So maybe I'm not knowledgeable enough to say that.
Thanks, Vahid. I think you've answered a lot of questions, and it's pretty getting late there. So thank you again for joining us on this really wonderful talk. And thank you all for coming. So we've had a lot of attendance from outside City College. So thank you all for signing up. And we hope to have more of these, but hopefully more in person. And Vahid, I owe you a dinner at